Hi, today we are going to talk about the exceptions to Octet Rule. Let's get started. So, what is Octet Rule? We already know. Octet Rule says that the valence shell must have 8 electrons, right? This is what is said by your Octet Rule, with exception of duplet for hydrogen, right? Now let us see some other exceptions that is played. And what are those? Most covalent compounds of beryllium. If you remember, hydrogen, helium, lithium, beryllium. Now, beryllium has an atomic number of 4, right? Now, you cannot expect beryllium to add 4 means 2 comma 2, right? You cannot expect 6 electrons to be added. Now, why 6 electrons can't be added? Because it's energetically very expensive, right? So beryllium will not look for 8 electrons. Instead, it needs only 4 electrons to satisfy its octet. Let's quickly look at an example. BeCl2. Remember, the first step was to find out the most symmetrical structure, and that is Be flanked by Cl on both sides. Now, the number of shared pair of electrons can be calculated by calculating N and A. So let's quickly calculate it N. Now, for N, what do you have? You have 2 atoms of chlorine, right? Chlorine wants 8, that is 16, plus beryllium, instead of 1 times 8, it will have only 1 times 4, right? So that comes out to be 20. Okay. Now A, what is A is the availability, right? Now for chlorine, you have 7, right? So 2 times 7, that comes out to be 14, plus for beryllium 2 comma 2. For the valence shell, you only have 2 electrons. So 1 times 2, that is 2, that is 16. So you need S is equals to N minus A, that is 20 minus 16 equals 4. Now we have to use this math to calculate the bonds here. We have to have 4 uh, electrons involved in the bonding, right? So let's quickly give, these are the 2 valence electrons of beryllium, and this will be the valence electron for chlorine. Remember, the remaining would be positioned as a lone pair. If you want to write that, you can simply write it as BeCl, Cl, and the remaining as lone pair of electrons, right? Now let us look at another example, that is for boron. Now, just like beryllium, boron needs 6, right? Just like beryllium, boron needs 6 electrons. So everything else is going to remain same. So first, most symmetrical structure with least electronegative in the center, which in this case is boron, right? Now here we have 6, so N equals, what do we have for N? We have 3 chlorine, 3 times 8 plus 1 times 6 instead of 8. In usual scenario, this number used to be 8, but here we'll have only 6, right? So that means 24 plus 6, that means 30. A equals your the availability, right? So 3 times 7, that equals 21, plus boron, hydrogen, helium, lithium, beryllium, boron 5, right? So 2 comma 3. So we have 1 times 3, that means 3, that means 24. So that means you need 6 shared pair of electrons, right? So those are the valence electrons of boron. Then you can have the valence electrons of chlorine written right there. The valence in front and the lone pairs surrounding, and those are the bonds, right? Another way to represent is simply BCl, Cl, and the lone pair electrons. just surrounding it, right? So that's the second exception. Now let's quickly talk about the third exception, that is the covalent compounds containing odd number of electrons like NO and NO2. Now you know the atomic number of nitrogen is 5, right? Oxygen is 6. 6 plus 5, you have 11 valence electrons available in the shell, right? Same goes for NO2 as well, right? N is 5, 2 times oxygen, that is 2 times 6, that is 12 plus 5, again 17. Hence, they will never be able to have um, a perfect formula just like the others, right? Most of the cases, compounds like these, they dimerize, and when they dimerize, they can easily satisfy the octet. So your NO2 dimerizes to N2O4 and NO2 dimerizes to N2O4 very easily. Now, the fourth exception would be the compounds with central atom with expanded valence shell. Now, what does expanded valence shell mean? Now, let's start with the same basic step. First, let's draw the most symmetrical, right? So, phosphorus in the center, because the least electronegative would be at the center. Then, fluorine all around it, right? Now, what's N? N is the total required, right? So, in case of phosphorus, it should be 8. In case of fluorine, 5 times 8, right? So that comes out to be 40, right? So you need 48 electrons. Now let's try to find out how many are available. So for 2, 7, fluorine, it has about 7 valence electrons, right? So we can easily write, we have 7 times 5, that makes out to be 35, plus phosphorus has only got 5, so that makes out to be total of 40, and S is equals to N minus A, that equals only 8 shared electrons, right? But as we can see, phosphorus has 5, right? And each fluorine is going to have 6, right? So I'm just gonna write 6 with 1 pointing towards this, just to make everything look very, very symmetrical, although not exactly required. Right now, as we can clearly see that we need one more, right? It's PF5. We need one more. 8 shared pair of electrons will not work, right? So we need to add 2 here. So this is the expanded valence shell, right? So phosphorus, instead of having 8 in its valence shell, needs to hold 10 shared electrons. But why is it even possible? Now, if you remember, S can hold 2, P can hold 6, D can hold 10, F can hold 14. What are S, P, D, F? They are orbitals, right? Okay, so as it happens, phosphorus does have d orbitals. So that is why it can accommodate, and that is why such valence shell exists. I hope this makes sense.
Thank you for watching this video. Don't stop now. Check out the next biology topic. More is coming. Subscribe and stay tuned.